Hi everyone, welcome to this episode of Keipert Labs. In this video today we're going to go through what we call the laws of constant and multiple proportions. Okay, so what we're thinking about here is this concept of the compound. Okay, so what we've looked at so far is this idea that we get a compound contains two or more elements, they are chemically combined. So chemically combined or bonded or fused or joined or however you want to put it, and in a particular way, so that they have distinct properties. That is to say that they are different. Their properties are different from the elements that came up to combine them. So we might say, e.g., H or O versus H2O. Okay, so that hydrogen and oxygen don't behave like water, which is made up of those two elements joined in a particular way. Now, one of the things that we've kind of taken as a bit of a given, or we've kind of stated, is this idea that that they always combine in a fixed ratio. Okay, as far as it's always H2O. We don't just kind of decide, all right, well maybe it's today it's H2O2 or H2O3 or H3O, or we don't just kind of vary it depending on the mood of the day. That there is some pattern or regularity in the way that they combine, and that helps us to define a particular compound as apart from any other. But what we're going to look at in this video is we're going to look at, all right, well, what evidence do we have that this is actually true? Okay, how did we actually arrive at this particular piece of knowledge? Okay, and so what we basically did, so what chemists going back to Dalton and thereabouts, is that they made very careful mass measurements. Okay, so remember that we've talked about this idea of the law of conservation of mass, okay, which was proposed before a concrete understanding of what where kind of Dalton was at. This idea that mass is conserved or mass is kind of maintained in chemical processes or in chemical change, that all the particles that we have there at the beginning are there at the end. And so what they could use this underlying principle that we didn't just kind of magically kind of vanish any mass, in order to then draw conclusions about how compounds were put together. So what they were able to do was to measure the mass of particular elements, and then versus when they were known to react together to make a compound. And then also vice versa. If we took a compound and then they were able to break it into its elements and then measure the mass of, or the quantity of the elements that were produced, and then kind of draw some conclusions from that. So very careful lab measurements to allow us to build towards this sort of idea. So in this particular activity, we're going to go through that sort of a process. Okay, so the first we're going to look at compounds involving the first thing that we're going to do, actually, I'll move it over a bit. Compounds containing carbon and oxygen. Okay, now so what we know, and this is kind of what we're building towards with this idea of the law of multiple proportions, is that some elements will combine together in different ways to make more than one compound. Okay, and so what we so here's something that we're presented with. Okay, so that after careful measurement of reaction of carbon and oxygen to make compounds, that we come up with two different sets of data, and saying that for every 100 grams of compound, for compound A, we have 57.1 grams of oxygen for every 42.9 grams of carbon. Okay, so for every 100 grams of compound A, we have that sort of ratio. And for compound B, we have 72.7 grams of oxygen for every 27.3 grams of carbon. Okay, so by careful kind of measurement of the amounts here, how much has reacted, how much is left over, all that sort of thing, being able to actually look at this. And so what chemists of the day then did was to actually look at these ratios, and what we recognize from people like Gay-Lussac and Avogadro was that they recognized that elements combined in fixed whole number ratios. Okay, that we didn't just kind of get 3/8 of this and 5/7 of this combined together. No, we got 1 of this and 2 of this. Okay, and so then what we could see is, all right, if we can get a ratio of the elements here, then that gets us somewhere towards explaining how these compounds are put together. And so, if we kind of compute this as a ratio, we get 1.33, and this one we get 2.67 or 2.66, kind of, when we look at that here. Now, what we can see is that B is equal to 2 times A. That is, this is double that. Okay, so if we take this ratio and we double it, we get in this sort of ballpark here. Now the other thing that we can notice is that we can actually, if I pick a different colour, because I like me some pretty colours, don't hate me, is if I express this as an improper fraction, that is, thinking about this as a ratio of how many particles of this to that, in terms of mass, I get 4 over 3, and here I get 8 over 3. You know, within, you know, if I kind of approximate it a little bit. Okay, recognizing that these integer kind of whole number ratios is a thing. Okay, so now, what I have to try and do is try to come up with 2 hypotheses to actually try and explain this. Okay, so this is what scientists do. We look at data and then we try to generate an explanation for it. Okay, well, what are some ideas that perhaps that could flow on from this to explain what we could see here? Okay, so the first hypothesis that we're going to work with and we're going to kind of map out is this idea that carbon and oxygen have equal mass. Okay, that atoms of different elements have equal mass. Now I realise that at this point you may well be howling in protest in your seat, thinking, "Sir, that makes no sense. We know this, we know that, but at the moment we don't know anything beyond this. We have not. These are 2 possible explanations. We have to weigh them up, and just, no pun intended, and then decide which is more reasonable." Okay, so we're saying, all right, well, let's imagine that carbon and oxygen are, as elements, have equal masses. You know, 1 carbon atom and 1 oxygen atom have an equal mass, and that there's something else that's fundamental about them that makes them different. Okay, and so what we can then say is, all right, well, one way we could account for this 4:3 ratio here is that we have 3 carbons for every 4 oxygens. Okay? So, if oxygen is our red circle and carbon is our black circle. Okay? So, we could say, all right, well, this ratio is, this compound is C3O4. Okay? So that would explain why we have 4 times the mass of oxygen for every 3 of carbon, that we have that many. And so then, okay, then it follows, so that B, we've got an 8:3 ratio. So let's say we've still got 3 carbons, but now we have 8 oxygens to account for the difference in mass. Okay, so then we're seeing that we've built these 2 different compounds. We've proposed a reasonable kind of formula for them that we kind of worked it through. Now the other hypothesis is that carbon and oxygen are not equal, okay, in mass, so that they have different masses, okay, and specifically what we're looking to say is not only are they different, but we've actually measured the ratio of them. That is, that oxygen is equal to is 1.33 or 1 1/3 times the mass of carbon. Okay, so that specifically we're saying, all right, well, that would kind of account for this ratio that we have here. And what we're then saying is, all right, well, if oxygen is always like this, then it should make the same thing for A and B, shouldn't it? That we're not saying that carbon and oxygen have that their masses vary from compound to compound, but that they may be different from each other. So let's say, all right, that actually the reason that we have this ratio is that we have 1 carbon and 1 oxygen, but that actually my oxygen is a bit larger in mass than my carbon, specifically 1 1/3 times the mass. Now I'm going to represent that with slightly different size here, okay? Because I can't really do it any other way. So then my formula that I would have here would be 1 carbon and 1 oxygen, okay? So then, if we're looking at this relationship, then how do we account for this? Well, let's say rather than having 3 and 8, we know that, okay, well, 1 1/3, you know, an oxygen is 1 1/3 times the mass of carbon, that B is double A. So maybe the way that we can account for it is actually to say we still have one carbon, but we now have two oxygens. Now they are supposed to be equal in size. Don't shoot me. And that actually we have this formula. So that this would account for why our second compound has a greater mass of oxygen. That the oxygen and carbon are different, but we now have two of them for every one carbon. So what we now have to consider is, okay, well, which is more reasonable? Okay, now, what we're going to do, just quickly, we're now going to quickly follow through the same sort of logic, looking at copper and oxygen. Okay, so here we go. We've now got this kind of same setup for two compounds of copper and oxygen. Okay, so same deal. Careful mass measurements, two distinct compounds that for every 100 grams of compound A, we have this ratio. For every 100 of compound B, we have this ratio. Okay, so when we do this calculation, we end up with a number of 3.97 and 7.95 when we look at these. So same sort of deal as before. We're going to now set these up as improper fractions. Okay, so that what we can see is that this is a number very close to 4, which we could then say is pretty much 4 over 1. To set it up as an improper fraction. This one's very close to 8, so we can say 8 over 1. Okay, so same as before, we're now, and so we could see here that B equals doubled A. Okay, so hypothesis number 1, same as before, that copper and oxygen have equal mass. And our hypothesis 2 will be that copper and oxygen have different mass. Okay, we'll go through and compute that in a second. Okay, so the way we could account for what we've measured in hypothesis 1 is that for every, so that we have 4 coppers for every 1 oxygen. So if I represent copper with a black circle, so then I'm saying, alright, so maybe I've got 1, 2, 3, 4 for every 1 oxygen, which I'll make red once more. Okay, so I've got a compound which is Cu4O. And then I get a value of 8 to 1, because then maybe I'll say, alright, I've got 8 coppers for every 1 oxygen, so I get Cu8O. That would explain the mass ratios, that if they had equal masses, that then that could make sense for it. Or then if we look at this and say, right, well then maybe they don't have the same mass, and then actually that mass is different by a particular ratio. That is, the ratio of copper is 4 times the mass of oxygen. Okay, so what we could then say is, all right, well then this mass ratio and this one could be explained by having 1 copper and 1 oxygen. That's kind of the simplest ratio we can get, but the copper has 4 times the mass. And so it would be just CuO. And then to go from here to here, double that to 8 to 1, okay, rather than making the copper 8 times as large and kind of saying that copper can change itself like that, is now we have 2 of our copper atoms for every 1 oxygen. And so Cu2O. Alright, so now with example 1 and example 2, what we can do is we can spend a moment to weigh up which seems more logical, which is a better explanation for what we've observed. Okay, does it seem reasonable that all elements, so carbon and oxygen, copper and oxygen, that should have the same mass? Okay, well, no. Okay, that's part of how we actually kind of can distinguish between elements, is that we recognize that their particles are different, that they have different masses. And so to say that copper is the same as carbon, is the same as oxygen, is the same as whatever, doesn't really seem like the best explanation. And likewise, what we can see with these is that the compounds in using hypothesis 2, the ratios are these compounds are much simpler, as opposed to these ones that they're much more elaborate. That you got 3 of this and 4 of this and 8 of this and 3 of this, and it gets very numerous. Whereas this is really simple. It's 2 to 1, 1 to 1. Okay, so what on balance then, that we would select hypothesis 2 over hypothesis 1, and suggest that elements have different masses, and that the difference in their mass can be quantified by looking at the ratio of their masses in compounds. Okay, so those two kind of key ideas. I pause and take note of those. Okay, so elements have different masses, and that we can quantify the difference. We can work out how much bigger or smaller they are by looking at ratios of their mass in compounds. Okay, so you need to go through and to continue the rest of the exercise with the remaining compounds. Use the same sort of idea to try and work out what's the simplest whole number ratio or relationship between elements in these compounds. Okay, thinking, you know, probably a good starting point is 1 of each would be the simplest kind of ratio you can get. Okay, just like we had here. Alright, thanks very much for watching. Okay, it'll be time for a chemistry joke now. Okay, so the optimist sees the glass as half full. The pessimist sees the glass as half empty. The chemist sees the glass as full, half with liquid and half with air. Thanks very much for watching. Bye for now.